An inductor of inductance 5.8 Henry and resistance 12 ohms is connected with a 7.2 volt EMF source. Now this inductor has some resistance. We can treat it as a series connection of a resistor and an ideal inductor. So this would be the equivalent of an RL circuit. The first question is, what is the initial rate of increase of the current? One way to solve this problem is to apply Kirchhoff's loop rule around this single loop circuit. We start from point A at the upper right corner and go in the counterclockwise direction. First, we go from the negative terminal towards the positive terminal of the battery, that's plus EMF. Then we're following the current and go across the resistor, that's a decrease in the voltage, so that's minus V sub R. And then we go across the inductor, which is also a decrease in potential. Why is there a decrease in potential? Now, if you think about the direction of the current in the circuit, it's counterclockwise. So for the inductor, the current goes from left to right and it's growing. The inductor will try to resist that change. If we had a battery instead of the inductor to resist the increase in current, the left-hand side terminal of the battery would have to be positive and the right-hand side terminal would have to be negative so that the battery can create a current in the opposite direction. And the inductor's terminals will follow the same order. So the inductor's terminal right now, positive terminal right now, is on the left-hand side and the negative terminal is on the right-hand side. That's because it has this nature of resisting the change in the current, and the current is growing, going from left to right. By Ohm's law, the voltage across the resistor is I times R, and the voltage across the inductor is L di dt. The reason I'm using absolute value signs around di dt is because I have already determined that voltage is dropping as I cross the inductor, so I want to keep VL positive. I already have my negative sign in front of it. Now note that initially at the very beginning the current will be zero. The current cannot change instantaneously in a branch or in a loop where there is an inductor. So before the circuit was connected, there was no current, and the moment it starts there is still no current. So I equals 0 initially. That's why the middle term goes away. And we rearrange our equation to isolate di dt, and we get EMF divided by L. Numerically, we get 1.2 amps per second. The next question is, what is the rate of increase of the current when current becomes 0.45 amps? We can use the same idea, same loop rule equation. This time current is not equal to 0 though, so we don't eliminate the middle term. When we rearrange our equation to isolate di dt, we get EMF minus I times R divided by L. Numerically, we get di dt equals 0.31 amps per second. Now we can see that the current is changing at a smaller rate than before. The next question is, what is the value of the current at t equals 0.15 seconds? Now time is given explicitly and we're looking for the instantaneous value of the current. Let's use the formula that represents the inductor's current as a function of time. Note that when you substitute t equals 0 in this formula, you get 0 as expected for the value of the current. And when t goes to infinity, the term in parentheses becomes equal to 1, and the current value becomes equal to EMF divided by the resistance. Now we're calculating an intermediate value for the current at some non-zero time, which is not infinity either. So when we plug in t equals 0.15 seconds, numerically we get I equals 0.16 amps. And finally, let's calculate the final steady state current, meaning the value of the current when t goes to infinity, a long time after the circuit has started. In that case, the second term in parentheses becomes equal to 0. Why is that? We have an exponential with a negative argument. So this value will be a negative large number. So the exponential value at a negative large number is equal to 0. So this term becomes 0. We get I equals EMF divided by R, which makes sense because a long time after, the inductor will act like a short circuit. Substituting the numerical values, we get I equals 0.60 amps. That is the final value of the current as it reaches a steady state and the current stops changing a long time after the circuit has started.